All right, welcome back to the online causal inference seminar. Today we are excited to have Isaiah Andrews from Harvard University, who will talk about inference on winners. After that, we'll have a discussion by Will Fithian. Questions today will be handled by Michael, so I'm now quickly switching over to him.
Thanks, Dominic. So we also have some collaborators in Q&A today, Toru Kitagawa and Adam McCloskey. So please submit your questions through the Q&A box. That's the Q&A box, not the chat box. Also, Isaiah will pause a couple times to receive questions live. So we may ask you whether you'd like to ask your question live. Just keep in mind, if you choose to do that, that the talk is being recorded. So with that, Isaiah, please feel free to start whenever you're ready.
Great, thank you very much. So thank you very much to all the organizers for the opportunity to present, and thanks very much to Will for discussing the paper. So today I am very excited to present the project Inference on Winners, which is joint work with Toru Kitagawa and Adam McCloskey. So in this project, we're interested in inference on target parameters chosen based on optimization. Right? Think, for example, of inference on the best performing treatment in an experiment. Not surprisingly, the data-driven choice of a target parameter leads to bias and undercoverage for conventional estimators and confidence sets, respectively. So to motivate what I'll be talking about today, I'm going to start by introducing the problem here in the context of the stylized example, where I'll describe the source of the bias and then sketch our corrected inference proposals. So for this stylized example, I'd like to think about a researcher who's running a randomized trial and estimating average outcomes under two treatments, say theta 1 and theta 2. The average outcomes under treatments theta 1 and theta 2, x theta 1 and x theta 2, for this toy example, will take to be jointly normal, centered at the population average outcomes under the corresponding treatment with identity variance covariance matrix, where again, I'm taking the identity variance covariance matrix just for the example, and we will be relaxing that in our more general results. So in this setting, right, given the results of such an experiment, we face a natural question of which treatment to recommend. And one natural option is to choose the treatment that maximizes the observed outcomes. So to recommend treatment theta hat, which is the argmax of x theta. Now, along with such a recommendation, we might also want an assessment for the effectiveness of the recommended treatment. And in particular, we might want estimates and confidence sets for mu theta hat, the true effectiveness of the estimated best treatment. In this setting, though, we run into a version of a winner's curse. Note in particular that theta hat is equal to theta 1 only if x theta 1 is greater than or equal to x theta 2. But this means the distribution of x theta 1, conditional on theta hat equals theta 1, is truncated below at the random truncation point x theta 2, which in turn means that the probability that x theta 1 overestimates mu theta 1, conditional on recommending treatment 1, is strictly greater than a half. Right, but the problem I've set up here is totally symmetric in treatments theta 1 and theta 2, so the same is true unconditionally as well. Right, so the unconditional probability that we overestimate the true effectiveness of the recommended treatment is strictly greater than a half. Right, so this says that our sort of conventional estimate for the true effectiveness of the recommended treatment is upwards median biased as an estimator for its true effectiveness. And at least in some cases, the corresponding confidence set, which just takes that estimate, adds and subtracts 1.96 standard errors, may undercover. So to see the extent to which this is a problem numerically, let's think about sort of a generalization of the toy example with 2, 10, and 50 treatments, where for simplicity, I'm still going to assume an identity variance covariance matrix. Let's further suppose that the first treatment is weakly more effective than the second, while all the remaining treatments are equally effective. Right, so here we're in a world where the first treatment is weakly most effective, everything else is the same. In this setting, let's think about the performance of the conventional estimator, right? So just sample average outcome for the recommended treatment, and the conventional or more pejoratively naive confidence set that just takes the conventional estimator, adds and subtracts 1.96 standard errors. So first, we could think about the overestimation probability. So in this plot, on the horizontal axis, I've got mu theta 1, the effectiveness of the first treatment, minus mu theta minus 1, the effectiveness of the remaining treatments. On the vertical axis, I'm showing the overestimation probability minus a half. So the probability that our estimate for the effectiveness of the recommended treatment exceeds its true effectiveness minus a half. What we see here is that when all the treatments are equally effective, we've got about a 75% chance of overestimating the effectiveness of the recommended treatment in the case where we're considering just 2 candidates. As I make the first treatment more effective, that overestimation probability drops and eventually converges down to a half. If I increase the number of treatments considered to 10, right, the overestimation probability when everything is tied goes to nearly 100%, but again, slowly declines as I make one treatment more effective than the other. Similar story with 50 treatments. If instead of thinking about overestimation probabilities, I prefer to think about the median estimation error, right, the picture is qualitatively similar, just the magnitude of the bias keeps getting worse as I add more treatments. Now, in addition to bias, we also care about coverage. So here I'm showing you the unconditional coverage probability of conventional 95% confidence intervals. It turns out in this case, if I have just 2 treatments, there's actually not an undercoverage problem. So the coverage of nominal 95% confidence intervals for the recommended treatment is in fact 95%. But if I increase the number of treatments to 10, the coverage probability when everything is tied drops to about 80%. Though it recovers as I make the first treatment better than the others. And if I increase the number of treatments to 50, the coverage drops to about 30%. So that was sort of hopefully convinced you that there's potentially a problem here trying to do inference on the best performing treatment in an experiment. I'll next talk about our solutions, but before I do that, let me just pause to see if there are any questions just about the setup so far.
We have no questions yet, so just continue.
Perfect. All right, so on to proposed solutions. So to think about correcting these issues, right, we need to say what we mean by correcting them. And we think there are at least 2 possible goals for corrected inference, but we'll focus on 2. So the first possible goal for corrected inference in this setting is what we'll term conditional inference. Right, so we might want procedures that are going to be valid conditional on the treatment theta hat that's going to be recommended. For confidence sets, for instance, this could mean conditional coverage. So the conditional coverage probability of our confidence set, conditional on recommending a given treatment, should be at least 1 minus alpha. For estimators, we could think about conditional median unbiasedness. So the conditional overestimation probability, again, conditional on recommending a given treatment, should be a half. Alternatively, though, we could also think about unconditional inference. Right, where rather than conditioning on the treatment recommended, we'll require validity only on average across different values theta hat that could have arisen. Right, so here we're saying we want something that's valid in whatever sense on average, but not conditional on a recommendation. For confidence sets, for instance, this would say that the unconditional coverage probability for the true effectiveness of the recommended treatment should be at least 1 minus alpha. While for estimators, we could have unconditional median unbiasedness. So the unconditional overestimation probability should be a half. Now, the law of iterated expectations tells us that unconditional validity is less demanding than conditional validity in the sense that any conditionally valid procedure is also valid unconditionally. But that means that the class of unconditional procedures is larger. So if we're satisfied with unconditional validity, we might be able to obtain unconditional performance improvements. Now, having introduced these 2 possible criteria, unconditional and conditional validity, it raises the natural question of which of them we ought to impose. And in our view, the answer to that seems fairly context specific. So to think through the distinction, let's go back to this toy example where it just got 2 treatments. And let's suppose that treatment theta 1 is some new treatment that we're considering. Treatment theta 2 is a control, right, which is sort of the baseline status quo. Now, if I impose only unconditional validity and the probability that I recommend the new treatment is small, then of course I may have that the coverage probability conditional on recommending the new treatment is much, much less than 1 minus alpha. And in particular, it may be the case that our confidence set is systematically over-optimistic in those cases where we recommend a new treatment, with the result that if one were to follow these recommendations that we're making, the results would lie below our confidence set with high probability. And one way to think about the conditional versus unconditional distinction is whether this sort of scenario bothers us. Right? If we say, yes, it bothers me that when I'm recommending a deviation from the status quo, the results are disappointing relative to the confidence set that I reported, then that says that we want coverage conditional on the recommendation corresponding to conditional validity. On the other hand, right, if we say, I've premised this whole discussion on the fact that the probability we recommend the new treatment is small, and so I don't worry about the fact that the coverage conditional on this low probability event is low, well, that would say that I'm satisfied with unconditional validity in this setting. So having set up those two potential goals, conditional and unconditional inference, what can one do in each case? So for conditional inference, right, we're going to be thinking about inference on mu theta hat, the true effectiveness of the recommended treatment, conditional on recommending treatment theta 1. But a useful observation here is that the conditional distribution of X, right, the vector of estimated average outcomes under different treatments, conditional on a given recommendation, is just going to be a multivariate truncated normal, right? But truncated normals belong to the exponential family. So using exponential family results, we can get optimal median unbiased estimators and equal-tailed confidence sets, where these confidence sets are equal-tailed in the sense that we're equally likely to over and underestimate mu theta hat. If you prefer uniformly most accurate unbiased confidence sets, those are also available and discussed in the appendix of the paper, as well as in the broader conditional inference literature. The intuition behind these constructions, right, is that in this case, where I want to do inference conditional on theta hat equals theta 1, mu theta 2, the true effectiveness of the treatment I'm not recommending, is a nuisance parameter, while x theta 2 is a minimal sufficient statistic for that nuisance parameter. But once we condition on that minimal sufficient statistic, right, the distribution of x theta 1 is just going to be a truncated normal, right? In particular, it'll be this untruncated normal distribution truncated to the interval where x1 is greater than the realized value of x2. So that's conditional inference. What about unconditional? So for unconditional inference, we've got two potential options. One, as I suggested before, is just to use the conditional procedure, right? Again, conditional validity implies unconditional validity. So we're free to just continue to report the conditional confidence set. However, since unconditional inference is a weaker criterion, we also have more options, right? And one option we could take is what we'll call the projection confidence set, which is an approach with many analogs in the existing literature. So for this approach, right, we'll just take our standard estimator, add and subtract a critical value, where this critical value will be the 1 minus alpha quantile of the max of the absolute value of a two-dimensional normal distribution. Right, intuitively, one way to think about what this confidence set is doing is it's forming a rectangular joint confidence set for mu theta 1 and mu theta 2, right, a simultaneous confidence set, and then projecting that on the dimension corresponding to the treatment of interest theta hat to construct a confidence interval for mu theta hat. Now, as it turns out, at least from our perspective, from the unconditional perspective here, neither of these confidence sets is fully satisfactory. As I'll show you in simulation in a minute, conditional confidence sets and estimators turn out to perform quite well when mu theta 1 is much, much bigger than mu theta 2, or the reverse, right? Sort of in the case where it's ex post going to be obvious which treatment is the best with high probability, but perform poorly when mu theta 1 and mu theta 2 are about the same. By contrast, the projection interval performs reasonably well when mu theta 1 and mu theta 2 are about the same, but ends up being unnecessarily wide when mu theta 1 is much bigger than mu theta 2. Now, if we require conditional coverage, right, I've already said that our conditional procedures are optimal. So if you're satisfied with the sense in which they're optimal, there's not really much scope for improvement here. But if we care only about unconditional coverage, right, then potentially there's scope to improve things. So in particular, to do that, we propose what we call a hybrid confidence set, which is uses an argument very similar to the conditioning approach, but changes the conditioning event. So rather than just conditioning on the recommended treatment, we also condition on the event that the true effectiveness of the recommended treatment lies in the level beta projection confidence set, where beta is some value less than alpha, and all the numbers I'm going to show you, we use beta equals alpha per 10. Changing the conditioning event in this way has the effect of ensuring that the hybrid confidence set always lies within the level beta projection confidence set, and so limits the worst case performance relative to the projection confidence set in this case where the two treatments are roughly the same, are roughly equally effective, while retaining most of the good performance of the conditional approach when one treatment is much better than the other. Building on similar ideas, we can propose hybrid estimators. And we find in simulation that hybridizing in this way seems to give substantial unconditional performance improvements in many cases. So to illustrate that, let's go back to this simulation example, where to avoid repeating the pictures too many times, I'm just going to focus on the case where we're thinking about 50 possible treatments. As before, we see that the conventional confidence set, right, dramatically undercovers when the treatments are of roughly similar effectiveness. The solid line here is the coverage of the projection confidence set. And we see that its coverage is right around the nominal level, 95%, when all the treatments are equally effective, but that it substantially overcovers, right, in this case where one treatment is much more effective than the others. Looking at the conditional and hybrid, by contrast, we see that their coverage is close to 95% uniformly across the different parameter values we're considering. In addition to coverage, of course, we also care about length. So here I'm plotting the median length of 95% confidence, nominal 95% confidence intervals. Right, of course, the length of the conventional and projection approaches doesn't depend on the realized value of x, right? So it's constant along the horizontal axis here. Looking first at the conditional, right, we see the phenomenon I was alluding to before, right? Basically, the conditional confidence set ends up being quite long, right? Its median length is more than twice the length of the projection interval, in this case where all the treatments are equally effective. As I make one treatment more effective than the others, right, its median length declines and eventually converges down all the way to the length of the conventional interval. Interestingly, in this particular case, taking this hybrid approach ends up giving us a median length that's shorter than the projection interval for all the parameter values we consider here. The median length of the hybrid converges almost all the way down to the length of the conventional interval, although it's hard to see here, the conditional will converge fully to the conventional. The hybrid doesn't quite get there, but it's close. So just to wrap up the takeaways from this stylized example, right, we first see that inference on the best performing treatment in an experiment invalidates conventional inference procedures. And of course, we're not the first to note this, as previously been noted by many others. To address this, we develop optimal inference procedures that are valid conditional on the parameter selected, but validity conditional on the parameter selected is also a fairly demanding criterion. So if we're satisfied with unconditional validity instead of conditional validity, we also propose these hybrid inference procedures, which we find allow substantial performance improvements relative to both our conditional procedures and an existing alternative, namely projection. In the remainder of the talk, I'll sketch sort of the constructions we're using for more general settings, and then illustrate all this with an application to the recent economics literature on neighborhood effects. Before I do that, though, let me just briefly flag the relation to the literature here. So, as I suggested, our optimality results for conditional inference build on classical results for exponential families. Further, results for conditional inference also build on the large and growing recent literature on selective inference, right? Where this literature develops a general framework for conditional inference that our conditional inference procedures fall into, where relative to this selective inference literature, one thing that appears to be new in this paper is that we find these substantial gains from relaxing to the unconditional problem via this hybrid approach. Our unconditional inference results likewise build on the large literature on post-selection inference, where the projection interval we use is a special case of procedures in this literature. But again, the hybrid approach appears to be novel relative to this post-selection inference literature. So before I move on to the more general case, let me pause here for questions.
Sure. Yeah, we have a question from I apologize if I'm pronouncing your name wrong, Kirkamo Mondet. So I'll allow you to unmute yourself.
Hello.
Hello. Hi. Yes, we can hear you.
Can you hear me?
Yes.
Yes.
So I have a couple of questions. So you just answered my second question, which is basically the connection to post-selection inference, basically. So the first question is, will the same problem arise if you decided to recommend the worst treatment instead of the best one?
Yeah. So it's totally, if you recommend the best treatment rather than the worst one, you could think of that as recommending the best treatment based on -x. So the results are totally symmetric for best versus worst. Related problems also come up if I say like, okay, maybe the best is selected, so I'm going to recommend the second best. Sort of the sort of exact form of the bias there is going to be a little different from the best, but sort of, again, you'll have bias and undercoverage issues in cases with a lot of treatments.
So when you have different, let's say, mechanism of recommending different treatment, maybe not necessarily the best, how this mechanism would affect your analysis?
Yeah, absolutely. So one way to think about it is, sorry, so I'm going to go back here. So just going to here, right? Essentially, one way to think about it is if you just give me some mechanism for picking which treatment I'm going to recommend, right? The event that I recommend a particular treatment, you can think of as an event in the space of X's, right? Basically the space of the sample average outcomes for all these different treatments. And so, right, sort of the more general version where you're not just picking the best, just you're picking in some way, you can think of as I'm interested in the effect of some treatment conditional on the event that X falls in some set in the space of possible X realizations. And that's precisely the sort of problem that the selective inference literature develops tools to address. And so conditional inference in that case is going to follow sort of the same logic as the selective inference literature. But the particular conditioning event would be different than the one we're using.
I see. Thank you very much.
Yeah, absolutely. Thank you.
Yeah, I think there's no more questions right now, so feel free to continue.
Perfect. All right. So with that, let me go and talk a bit about our more general results. So sort of moving beyond this toy example, the more general setting we think about is one where we observe vectors X and Y, which are jointly normal with unknown mean mu, known covariance matrix sigma. Note that unlike in the toy example, sigma doesn't have to be diagonal. These things don't have to be independent, anything like that. We'll again index the elements of X and Y by theta, right? Writing mu X theta for the mean of X theta, mu Y theta for the mean of Y theta. Now, in today's talk and in most of the paper, we focus on this finite sample normal setting with a known variance matrix. But in the paper, we show that finite sample results in the normal model translate to uniform asymptotic results in the way you would expect in cases where I've got asymptotically normal X and Y and a consistent estimator for sigma. So if you prefer to think about these as asymptotic results, you can do that translation. Now, for the general problem, we'll suppose that we're going to pick theta, again, as the argmax of X theta, but that we're interested in inference on mu Y theta hat. Right, so this is a generalization of the stylized example because we're allowing the possibility that we're doing selection based on one thing and targeting inference based on another. Right, for instance, maybe I'm interested in picking the best performing treatment in terms of average outcomes over everybody, but I want to do inference on the impact of that treatment for some subpopulation of interest, right? And that's going to be accommodated by this setup. Now, for conditional inference, the construction from the toy example extends directly to the general case, but I'm going to refer you to the paper for sort of the gory details of that. At the end of the day, the upshot is that we'll get an optimal quantile unbiased estimator, mu hat alpha, right, where the probability that we overestimate the true effectiveness of the recommended treatment, conditional on the recommendation made, is going to be exactly equal to alpha. Hence, mu hat 1/2 is going to be a median unbiased estimator, while the equal tailed interval, mu hat alpha over 2 to mu hat 1 minus alpha over 2, will have coverage 1 minus alpha. It further turns out that in cases where the probability that theta hat takes some value theta tilde is close to 1, right? Where I almost don't have a selection problem because I almost always pick the same treatment, right? This is in the plots in the toy example. This was when treatment 1 was much, much better than the other treatments. The median unbiased estimator is approximately the same, in particular converges to the conventional estimator, while the equal-tailed confidence interval collapses to the standard normal confidence interval. Right, and so in that sense, these corrections from the conditional approach vanish in the case where they're not needed. Now, I do want to say a word on a common alternative to, or one natural solution to deal with this issue, which is sample splitting. So for sample splitting, you could think, for instance, of choosing theta hat based on the first half or other fraction of the data, while using the other half or other fraction of the data for inference. Asymptotically, what this looks like, right, is getting independent x1, y1 and x2, y2, where I'll calculate theta hat based on x1 and then use y2 for inference. Now, since x1 and y2 are independent, right, selecting the target parameter based on x1 doesn't mess up inference based on y2. So conventional inference is going to be valid in this setup. But results in Fithian, Sun, and Taylor 2017 say that sample splitting is going to be dominated for this problem. Right, and one way to think about the reason why is that rather than conditioning on theta hat equals theta tilde, right, if I take the sample splitting approach here, I'm effectively conditioning on the pair x1, y1. Right, but there's still some residual useful information in x1, y1 conditional on the realization of theta hat. And so by exploiting that information, one can develop more powerful inference. And so in the supplement to the paper, we talk about one easy to compute split sample procedure that dominates the usual split sample approach. Now, if you think about sort of splits, this like doing a split sample type of thing versus the approach I've been sketching so far, which is using the full data to select X, right there, you face a bit of a trade-off, right? Because using sample splitting leaves more information for inference on the parameter of interest, but on average, right, you'll do a better job picking the best treatment if you use more of the data for that, right? And so that raises a question of how do you feel about sort of picking the best treatment possible in expectation versus doing a better job on inference. Next, we can also generalize our results for unconditional inference, right? For unconditional inference for the projection approach, we'll again just form a rectangular joint confidence set for the full vector mu y, and then report the interval corresponding to the parameter of interest mu y theta hat. And again, the hybrid approach is just going to combine the conditional and projection ideas, exactly analogous to the toy example before. So that's a quick sketch of our results for the more general setting. Any questions at this stage?
Not currently, no.
Perfect. So to wrap up, I want to revisit, illustrate with a analysis revisiting the recent economics literature on neighborhood effects. So Chetty and Hendren 2018 find that the neighborhoods in which children grow up appear to have large causal impacts on their outcomes in adulthood. Motivated by these results, Bergman et al. 2020 conducted a randomized trial trying to help low-income households with children move to higher opportunity neighborhoods. Right, they were doing this in the conjunction with the Seattle and King County housing authorities in Washington State, and the target neighborhoods here, the neighborhoods they were trying to help these low-income families move to, were defined roughly as the top third of census tracts in the Seattle commuting zone based on estimated measures of economic opportunity. Right, and for the exercise I'm going to show you here, we asked what would happen if one were to repeat this exercise in the 50 largest commuting zones in the US. And I'll show you both simulation and empirical results in this setting. So for simulations, what we're going to do is to treat the neighborhood level economic opportunity estimates used by Bergman et al. 2020 as the true values of this economic opportunity measure. Right, we'll then simulate estimates by adding noise with standard deviation equal to the standard errors for the original measures. In each commuting zone, we'll then select the top third of tracts based on these simulated estimates, and we'll conduct inference on the average quality of selected tracts relative to the average over the whole commuting zone. right? So we're essentially trying to estimate the extent to which targeting tracts in this way is succeeding in selecting higher quality tracts on average. For both the simulation and empirical results, I'm going to include a comparison with empirical Bayes estimates and credible sets. Right, and one reason for doing this is that empirical Bayes estimates based on a normal prior are widely used in the applied literature in this area, and so are a natural benchmark. Right. Plus, of course, if you if one were to take a fully Bayesian approach, right, if I specified my prior over the distribution of economic opportunity, under that prior, this selection issue goes away, right? Since Bayes is valid conditional on the full data, so it's certainly valid conditional on the best performing treatment in the experiment. So let me show you some results in this setting. So panel A here, I'm showing you the gains from selected tracts on average across each of these 50 commuting zones. So the units here are that an effect size of 0.05 says that if one takes this model of neighborhood level economic opportunity seriously, right, we think that for children growing up in households at the 25th percentile of the income distribution, moving to a randomly selected target tract relative to a randomly selected tract over the entire commuting zone is going to increase that child's rank in the income distribution in adulthood by 5 percentage points. Right, so these are non-trivial effect sizes here. We see that across all 50 commuting zones, these numbers are positive, which is saying that, again, under this model, we are succeeding in selecting higher quality tracts on average by doing things in this way. Panel B shows the median bias of various estimators, right? So the green here is the naive estimator, which just ignores the selection issue. Not surprisingly, it's upward bias for exactly the reasons we already discussed. In red, I've got the empirical Bayes estimator. Interestingly, right, doing empirical Bayes shrinkage off of the normal prior here definitely reduces the absolute magnitude of the bias and makes the sign ambiguous, right? We're biased upwards in some commuting zones, biased downwards in others. Finally, the conditional and hybrid are in blue and gray here, and as we would hope, are close to median unbiased. Panel C here, I'm showing the median absolute estimation error. So here we see that the naive does worse than the conditional and the hybrid, which overlap here in the blue, which in turn does worse than empirical Bayes. Right, so if all I cared about here were median absolute estimation errors, I don't care about bias, I'd actually be better off doing empirical Bayes in general here. Panel D here shows coverage. Right, so we see that naive confidence intervals dramatically undercover across all 50 commuting zones. Empirical Bayes credible sets, the coverage actually varies a great deal across different commuting zones. So in some it's extremely low, in some it's actually close to 95%. Projection intervals overcover, while hybrid and conditional intervals have coverage close to 95% across all 50 commuting zones. Finally, panel E here, I'm showing you the median length of these different intervals. So we see that conditional intervals are generally longer than projection intervals, which are longer than hybrid intervals, which in turn are longer than naive and empirical Bayes intervals, although the latter two undercover. Finally, here I'm showing you the empirical results from applying all this to the actual data. So in green, I've got the naive estimator and confidence interval. In blue, the hybrid estimator and confidence interval. Red, the empirical Bayes estimator and credible set. And orange, the projection interval. One thing we note is that across all 50 commuting zones, the hybrid and empirical Bayes estimates shift the naive estimates downwards. So, according to both those approaches, we do want to correct things downwards here. The hybrid intervals are, not surprisingly, substantially wider than both the empirical Bayes and the naive intervals, but substantially shorter than the projection intervals. Also worth noting, even with these, even correcting the estimates downwards here, the hybrid and projection intervals here never overlap 0, right? And so that's saying that even taking into account the presence of this sort of winner's curse bias, we still conclude that, again, taking the neighborhood effects model seriously, targeting neighborhoods in this way is succeeding in selecting higher opportunity tracks on average across all these commuting zones. So to wrap up, in this project, we're interested in inference on parameters chosen based on maximization, which leads to bias and undercoverage if not corrected. For this setting, one can get optimal inference and median unbiased estimators conditional on the parameter chosen, right, where these conditional procedures converge to conventional ones in the case where the corrections are needed because the same thing is selected with high probability. If we only care about unconditional bias or coverage, we can also think about these hybrid confidence sets and estimators, which we find outperform both pure conditional procedures and the existing alternative in the literature, namely projection. So that wraps up what I wanted to say.
Thanks so much, Isaiah. Maybe we have one final question. So this comes from an anonymous attendee. It reads, could cross-fitting further improve the inference procedure in comparison to sample splitting?
So we've thought about it here, and the thing that ends up being a bit tricky with cross-fitting in this case is sort of what treatment are you making a statement about, right? Because if I I split the data and I sort of pick a treatment on part one of the data and then create a confidence interval on part two and then flip the two roles, right? I've got two confidence intervals, but in general, those may be confidence intervals for the effects of different treatments, right? And so in some sense, it's sort of there, you end up with confidence intervals, but it's not the conditional approach where you use the full data or where you just do sort of direct sample splitting and don't do the cross-fitting thing, you end up with a recommendation and then a confidence interval that corresponds to that recommendation. In cross-fitting, you end up with multiple recommendations, and so you sort of lose that interpretive element in a way that, at least to us, made it unclear how to think about the results from cross-fitting in this setting, or sort of whether that would be something attractive to do.
Great,
All right, thank you so much. Yeah.
Fantastic.
Yeah, so we're now switching over to the discussion. We'll have Will Fithian present some slides, and after that, you'll have, Isaiah, you will have the opportunity to respond. Will, whenever you're ready.
Great, can you hear me?
Yep.
Okay, so thanks very much, Isaiah, and thanks so much to the organizers. So I'm Will Fithian. So there's a lot to like about the paper and the talk. I really enjoyed reading it. So one thing I think sometimes we don't spend enough time talking about in statistics is the difference between these different goals. And I really like the discussion of conditional versus unconditional inference goals, although I'm not sure that it left me any less confused about which I should use. So I don't mean that as an insult. I'm not sure that it's possible to make me less confused. I really love the hybrid method. It's simple in the best possible sense of the word. We should have thought of this a long time ago, but it's really exciting, and it kind of trims the wild tails of the conditional C confidence intervals that we worry about. I'll talk a little bit more about that later. I like the median unbiased estimator. There's also the uniform asymptotic results that are difficult to get for the purely conditional approach. I'll start with just a sort of, so the winner's curse can be, so it sounds very obvious, but it can actually be, there are surprising phenomena. So as Isaiah mentioned, there isn't actually undercoverage if there are only two treatments. So how could this possibly be? Well, there's a nice recent paper by Yotam Hecklinger, Yoav Benyamini, and Philip Stark, and they show that you can think of it as a method that has this very weird acceptance region. So here, this is the region where, if you can see my mouse, this is the region where we choose treatment number one, and these are the times when we choose treatment number one and we get we don't cover if this is mu, and the same over here for treatment number two. And if we just flip this region, we just get the usual shape. So it's interesting. Sometimes you find that you don't actually need corrections, but of course, most of the time you do need corrections, as Isaiah showed. I think a big motivation, or probably the main motivation for the hybrid method is, especially in the case where we have a one-sided truncation event, the conditional intervals have serious problems. So, you know, as I mentioned, they are optimal as conditional intervals, but that definitely leads us to question how committed are we to following this conditional approach. So here, if we have normal mu1 truncated to just be bigger than 3, then if we observe a y that's significantly bigger than the boundary, then we just get back the nominal intervals. So that's a really nice thing about the conditional approach. But as we get close to the boundary, if you think about it, if you observe 3.1, can we reject that mu is -5? Well, actually, no, because even if mu is -5, conditional on y being bigger than 3, it's not that unlikely that y would be 3.1. And so that's why mu equals -5 has to be included in this confidence interval. I should note that if we randomize, or other shaped regions, so of course, you know, this is one application of conditional post-selection inference, and other applications behave much better. So this can be fixed by data splitting, as Isaiah alluded to, or we sort of call it data carving, because we do data splitting, but then we use sort of the leftover information in the first data set. So here we truncate. So now I've split the y into 2. I truncate to just the first one being above 3. And now the confidence interval, the expected confidence interval length is bounded above by what I would get by data splitting. And so this has some of the nice properties of the hybrid approach, but there is a problem that the hybrid approach doesn't have, which is that we're only using part of the data. And if we're trying to select the best treatment, then it's much more appealing to use all of the data to select the best treatment. So the hybrid method, so it's more complicated than this, but I think roughly we construct simultaneous confidence intervals for each of the treatments. We just sort of assume that they cover. This is a time-honored tradition in multiple testing. We do something, we assume that it worked, and we go from there, and then we kind of we get to clip the conditional interval there. So here, you know, if there's 50 treatments and we're using alpha over 10, then the half width is 3.7, and so now if mu were -5, we would never even have been in this situation to begin with. And at least with probability 99.5, and that justifies excluding -5 from the interval. So this is a totally simple idea, totally solves the problem, at least unconditionally, and it's so simple that it makes you think that it could be applied anywhere. I don't know exactly how I would just plug this in if I were doing post-selection inference and regression, say, but I'm curious just sort of how how easily generalizable this is, or how would we turn this into a general principle? Because I would like to do that. Maybe you've already done it. And also, is this approach complementary with the randomization approach? Is it one or the other, or could we combine them, and would it be fruitful to combine them in some way? Okay, so the other thing is, well, we can reject mu as -5, but we could also reject mu as 6.8. That's 3.1 plus 3.7. But we actually could already reject that mu as 6.8. So it doesn't seem like we've gained anything on the top end. We certainly gained by clipping the bottom end, but we didn't need to clip the top end. So I wonder, would it be more efficient to use, of course, I've described a simpler version of what they're actually doing, but I wonder, would it be more efficient to use just lower confidence bounds instead of confidence intervals for the initial step? And second, it doesn't seem like we need to worry too much if we're constructing a region for mu1, mu2, mu3. We don't have to worry too much about rejecting mu1 equals 11 and mu2, mu3 are -11. That the conditional intervals are going to do perfectly well there. So I wonder, by sort of very carefully crafting regions, could we converge to the nominal interval? Could we recover this very nice property of the conditional intervals as the selection becomes really obvious? Okay, and the last thing is that the housing example, so really, really nice example. They're comparing their method to an empirical Bayes method that we have, it looks wonderful. So when I see these intervals, I'm very resistant to getting rid of them and going for the blue ones. And you know, so these red intervals, they're using information census level, census tract level covariates to make predictions, and they're assuming that those predictions are mostly not too wrong. And they're sort of estimating how wrong they are based on the data. Excuse me. So we see these, and we would really love to keep using them, but you know, Isaiah and Toru and Andrew tell us that they undercover. So it seems like, what can we do? I wonder how much of the undercoverage, so it could be model misspecification for the prior, as they mentioned in the paper, but I wonder, is there something about the goal being different? Because these are credible intervals rather than confidence intervals. And so they guarantee us coverage given the data, they don't guarantee us coverage given the parameter. So given the data, if we think of the parameter as random, then the credible intervals will cover. If we generate the data and the parameter jointly, then we will get coverage. But there's sort of, but the simulation in the paper is sort of a quasi fixed effects model where the good census tracts basically get to keep their effect sizes are jittered a bit, but they basically get to keep being good fixed effects. They basically get to keep being good census tracts. This is a little bit like the issue that was brought up by Efron and Morris in their 1977 paper on the James Stein estimator, another empirical Bayes method. And they noticed that this shrinkage is doing well, and they have better performance in some ways, but they say, well, maybe we're not being fair to Roberto Clemente, who was a big time all-star. And you know, we shouldn't be surprised that he's doing better than these other baseball players. So why are we assuming that he's no better than the others? And so in particular, we wouldn't expect, if we repeated this experiment many times, to be covering for Roberto Clemente. And so I wonder if all the census tracts that we're looking at here are just all the Roberto Clementes. And if that's the case, then it sort of raises, well, one question is sort of, you know, either is empirical Bayes doing what it's advertised, but we just don't like it? Is it possible that there's something about empirical Bayes that's just not answering quite the right question for inference on winners? I don't know the answer to that question, but I'm curious what you all think of it. And finally, so this census, they're getting a lot of mileage out of using the census tract covariates. So I wonder if there's any way to bring those into the analysis, the frequentist analysis. So here I just have the questions up on this slide, and I'll mute myself and look forward to hearing the response.
Fantastic. Thanks so much, Will, for the really, really great discussion. And thank you as well for collecting the questions. No, these are great questions. So to go through them in order, I guess starting with the first one on whether it can be applied anywhere. In some sense, I think our view is that the answer seems to be yes, subject to, you know, not having done it absolutely everywhere. But so certainly just this idea of, you know, if I've got some unconditionally valid interval, I can combine it with can sort of use it as the basis for a conditional interval via this sort of hybridization argument, seems to work more broadly. And Adam, my co-author on this, has one of my co-authors on this has a separate paper thinking about that in model selection settings. And so at least there, it does seem to extend. It seems to extend there at least. On complementing with randomization, yeah, again, I think it's a super interesting question and not one that I feel like I have a super solid answer on at the moment. I guess my sort of, for this inference on winners setting that that's sort of our focus in this paper, exactly as you were saying, randomization feels potentially unappealing in that I'm sort of paying a price in terms of the, you know, quality of the recommendation I'm generating in exchange for doing a better job on inference on that object. And so there, it's not entirely obvious to me one would want to go that direction, but certainly for more general model selection settings, I think there's potentially a lot of appeal. And I mean, one could also take a different view even for the inference on winners case. On 2A, yeah, absolutely. So in the context of the toy example where all basically you only end up with lower truncation, it's definitely going to be more efficient to use simultaneous confidence intervals. As you of course know, for more general covariance structures here, you can end up with both lower and upper truncation, which is why we sort of defaulted to the two-sided projection interval, but one could absolutely do something more tailored and get power gains from sort of choosing the initial unconditional interval that is the basis of the hybrid method in a more careful and case-specific way. Absolutely. Very much, very similar answer on your 2B. I guess we have not thought through sort of whether exactly what one would need to do to get an oddly shaped region that's going to converge, that's going to ensure full convergence to the nominal interval, as we have a very, very clear winner for the hybrid case. But exactly as you're suggesting, it seems that there should be a way to do that. And my many apologies to someone if there is one out there that we just are not aware of at the moment. But it does seem like it should be possible to do something along those lines, and then to combine that with the hybrid interval so you're not paying sort of this price at infinity when there really isn't a selection issue. On question 3A, is empirical Bayes appropriate for inference on winners? Yeah, again, I think it's a really interesting question, and the way that we had thought about this is starting from the observation that if I were in a fully Bayesian world, right? So I specify my prior on the distribution of tract level effects. And in fact, tract level effects are drawn from that prior distribution, then, right, there is no inference on winners problem, right? So the coverage probability of my credible interval for the winner under that data generating process is precisely the nominal level, again, by iterated expectations. And so in that sense, the way we were thinking about the sort of empirical Bayes under coverage we were observing in these simulations was basically about a divergence between the underlying distribution of effect sizes and that data generating and sort of the normal distribution assumed by the prior. Now, if one were to sort of, as you noted, sort of there are two layers to that, right? So one is that in our simulation designs, we are holding the tract quality fixed. And so that's certainly a departure from redrawing it from a normal distribution. At the other extreme, we could, of course, redraw it from a normal distribution, in which case, up to estimating the prior hyperparameters, my guess is that empirical Bayes should have coverage, very, 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 very good coverage. There's then this intermediate ground of, what if we fit some sort of a non-normal distribution to the tract level economic opportunity estimates and redraw from those. And that is not a middle ground that we've explored yet, but I agree it's definitely interesting to think about. My intuition would be if it's highly non-normal and we insist on doing normal empirical Bayes based on a normal prior, we should still get issues, but of course one could also do empirical Bayes based on a richer class of priors. And I think there's a very interesting space to explore there. And on your final question, whether one could use census tract covariates, again, yeah, that is an interesting question. Whether one could use census tract level covariates for the frequentist analysis, that's a quite interesting question, and one that it certainly seems like there should be a way to do it. It is not something we have done, and so I don't want to speculate too much on the ideal way to do it, but it's a super interesting question that we definitely will want to think about. So thank you so much for the really great discussion and great questions, Will. Thank you again.
Thank you.
All right. Thank you so much. If there are no further comments, I will now quickly wrap up.
I think Hito has a question.
Oh, okay, sure.
So, yeah, Isaiah, this is very interesting. I was wondering whether this relates to some of the multi-arm bandit things. Because there you also obviously have issues with inference, and I think there people have kind of tried various ways of trying to get confidence intervals given the designs, given the adaptive designs. So
yeah, so this is early stages, but actually have been talking with a student, Kevin Chen at Harvard, about some related conditioning ideas and settings like multi-arm bandits, where you're or sort of adaptive randomized trials with large batches where you're willing to treat things as approximately normally distributed. It does seem like some ideas related to the conditional inference machinery we're building on here do appear to extend to some settings of that sort, although that is very much early stage discussions at the moment. But it does seem like there are things that one can do in that general direction, building on similar ideas.
All right, thank you. Yeah, then, yeah, thank you everyone. First, thank you, Isaiah, for a very interesting talk, and Will for a very nice discussion. Also, thank you to Toro and Adam for helping out in Q&A. Next time, we're going to have a talk by Alex Wolfowski from Duke University. I hope I pronounced that correctly, who will talk about online experimentation for studying political polarization. Thank you all for coming, and hope you have a great week, and see you next time.